Okay. I'm sorry, online folks. I forgot to unmute. I just introduced Doug, and he just got started.
Okay.
Thank you again.
So I'll talk a little bit about what a surface is in terms of the surface modeling itself, because that's important when you talk about this surface-based, boundary-based registration. Um, Obviously, if for fMRI analysis, you want the best registration that you can have. And this is especially important for cortex because cortex is only about 3 millimeters thick. And so, the 3 millimeters is not very much. So if you're off by even a little bit, then your multimodal integration is going to be off and you're going to be drawing incorrect conclusions from your data. And for laminar, of course, you're not talking about 3 millimeters, you're talking about 1 millimeter or a half millimeter, something like that. So the requirements for accuracy in your registration are even higher for laminar analysis. So there are some challenges when you go to try to register your function and your structure. So there are issues with bias fields. So as you saw in the previous presentation, MR has like these bias fields where you have, generally brighter at the very edge of the brain and often quite dark at the center of the brain. And so these can create issues. For when you're scanning at very high resolutions, you often have partial volume, or partial fields of view. So you're not collecting an entire brain, you're collecting like a slab of an entire brain. And so registering a slab is going to be harder than registering a whole brain. And then, of course, you have distortion issues when you have fMRI, B0 distortion, maybe other kinds of distortion that you don't really even know about. So I'll talk about boundary-based registration. So this is something that Bruce Fischel and I developed and published in 2009, I think it's been. And since then, it's been adopted by FSL and Brain Voyager, and I haven't seen it in FSL in SPM yet or AFNI. And then I'll talk about the effects of varying certain parameters in the BBR algorithm. And I'll talk about B0 distortion and how this is handled in BBR. So, you've probably seen images like this many times already. You've probably produced them yourselves, but just to get everybody on the same page, this is the T1 anatomical, and then the yellow line is the white surface, which is shown here in 3D, and the blue line is the peel surface, which is shown here in 3D. And then this is the inflated surface that shows you that this is just not some like arbitrary structure in 3 dimensions, that is actually a 2-dimensional structure that's embedded in 3 dimensions. And this is, you look at these images and you kind of forget like what is behind them. And what's behind them is this mesh model. So what we do is to create these little triangles that we essentially glue on the outside of cortex. And where those triangles meet is a vertex. And so a vertex has certain properties to it. It has an XYZ location. It has a certain neighborhood around it, vertices that are around it. And so once you have that information, then you can create this mesh of the surface. And this is a topology, this is a geometry that allows you to compute things like thickness and surface area and distance from one point to another. And so this is going to be critical when it comes to actually integrating this structural analysis with your functional analysis, because you want to be able to use all this information from this high resolution structural imaging with your slightly lower, perhaps lower resolution fMRI. And so the first step in the integration is the registration between the structure and the function. So this assumes that you've run something like FreeSurf or Brain Voyager or CAT to create surfaces. And you have surfaces from the anatomical that are in the form of this mesh model. And so you have your fMRI, which might be done in the same session. It might have been done in a different session. So people were talking about doing your anatomicals at 3T and your fMRI at 7T. So even if when they're done in the same session, you can't count on the possibility that the person has kept their head in the exact same position, given that you need to register the anatomical and the functional to within a millimeter or half millimeter or something like that. It's really, really easy to move your head by that amount. So there's a need for registering the anatomical and the functional, and that's done through these registration algorithms that have been developed over the last 20, 30 years. And so the basic idea is that you can move your head in 6 different ways. So you can move your head left to right, you can move your head forward and backwards, move your head up and down. You can shake your head yes, you can shake your head no. You can do this, which is maybe, I suppose. And so the basic idea with registration is that you would take the fMRI and you would apply some transform to it that would be some indication of what these 6 parameters are. And then you would overlay it on the anatomical, and you sit there and play with those things until you get the best alignment in some way. And then once you have the alignment, then you can map the surfaces onto the fMRI, and then you can sample the fMRI onto the surfaces, and then you can start doing your surface-based fMRI analysis, be it just like a cortical-based one or like a single layer of cortex or this laminar analysis. So a question comes up as to what the registration algorithm is going to be doing, because what it's going to be doing is computing some kind of cost. So for each instantiation of those 6 parameters, you're going to get some alignment between the anatomical and the functional. And so for that alignment, you have to compute some type of cost. And then the idea is going to be that you're going to change, the computer is going to change this alignment to follow the cost down to try to minimize that cost. And so up until the time of BBR, the way that this was done was just to look at every voxel in the brain. So you would take the functional, you would apply your putative transformation to it, and you get some alignment with the anatomical. And then you'd look at voxel for voxel, and you look at every single voxel in the brain, and you'd do some comparison between them, and you would get some cost out of it. But what Bruce realized, back in 2008 was that this is not the best way to do that. That really, there are only a few voxels in the brain where you're actually getting interesting signal. And that's at tissue type boundaries. So at the boundary between white matter and gray matter. And so that's really where the best place to get the signal is. Also, cortex is very highly folded, so you're getting like this very complicated signal that's spatially very complicated. So you get high contrast and a spatially very diverse signal around it. The other reason for looking only around where cortex is that you don't have to worry about brain masking. So when you're doing an alignment between, say, fMRI and the anatomical, traditionally what you have to do is to do a skull stripping of both the anatomical and the functional. And unless you do that exactly the same way, you're going to have places where maybe there's a little bit of eyeball left in the anatomical, or maybe a little bit of brainstem left in the functional, and the actual outer edge of the brain mask in both of these things is not going to be the same. And that can be something that corrupts the registration. So when you're driving the registration, the cost function off of cortex, you don't actually need to do any brain masking at all. And in addition to this, we'll talk about that later. And when you register cortex, even though you're using these few voxels, you're actually getting good registration everywhere because you're assuming that there is a rigid or affine registration between the two. So this is what we do in BBR. So what you're looking at here is a zoom in of an fMRI volume, a slice through an fMRI volume, resampled to 1 millimeter using trilinear interpolation. So in reality, the fMRI is, in this case, is probably something like 3 millimeters, maybe even more. And so I've overlaid on this surfaces. So this white line here is the white surface. This black line here is the peel surface. So everything in between is gray matter. So white matter is here inside of the white matter surface. And then what I've labeled here, central sulcus, is actually CSF. So as I mentioned before, the surface is actually modeled as these discrete vertices. And so I've kind of indicated them by these little circles here. And at any given vertex, we know the tangential plane around cortex, so we know what the normal is to that. So if I go to any given vertex, I know what the normal is with respect to that. And so all we're going to do is to take, start at this vertex and project into gray matter a little bit to compute, to sample the fMRI at that particular location in gray matter. And we're going to project back into white matter to compute the value there. So I have that as WV and GV. And so then we're just going to compute a contrast, which is gray matter minus white matter divided by gray matter plus white matter, essentially. This is a percent contrast at that particular location. And so one of the nice things about using the contrast here is that it's almost completely immune to bias fields. So these bias fields where you see that the outside of the brain is very bright and the inside of the brain is very dark. This will throw off whole brain methods rather substantially. However, when you compute this contrast, you know, these 2 points are only like 2-3 millimeters apart. And so when you compute that contrast over such a short span of space, you actually don't have to worry about the bias field, because the bias field is generally pretty slowly varying over cortex. So it becomes very insensitive to these bias fields. So once we have that contrast, then we put it into this nonlinear function here, which is implemented as a hyperbolic tangent. So as you increase the contrast, the cost is actually dropping, which is what you want, because when everything is like perfectly aligned, then at every point in cortex, the contrast should be high, and so the cost should be low. And then where the contrast is zero, what does the zero contrast mean? It means that on either side of the surface, you have the same tissue type, which is not what you want, because the surface should be on the boundary of the tissue type. So when the contrast is at zero, we have a cost of 1. And if the contrast is actually going in the opposite direction, it means that your registration is really off. So the cost will go up to 2. So at every vertex, we compute a contrast, and then we put it through this nonlinearity to get the cost at that vertex. And then we just sum them up to give you one single number, which is the cost for that particular registration with those particular parameters. And so then it's just a game of trying to go down a hill, this cost hill. This, if you think of the cost as a landscape, you have 6 parameters that you're trying to optimize, and simply adapt those parameters to follow the cost down the cost gradient. So there are several parameters that are here. So there is this delta WV, which is the distance that you're going to project from the white surface to the place where you're going to sample it. And then there's delta GV, which is the distance from the white surface into gray matter. There's this M value, which I haven't really talked much about, which indicates the sharpness of this nonlinearity. There is the interpolation method that you're going to use. So it could be nearest neighbor, it could be trilinear, it could be cubic. There's a question of how densely you're going to sample. So you can sample every single vertex, or you can skip every, say, second or fourth vertex to speed things up. And then there are also regions that you can exclude. So you remember with FreeSurfer, we're doing a cortical-based segmentation. So what comes out of the anatomical analysis are like all of these different regions of interest that you have on cortex. And some of those are known to be, say, high myelin regions where you might not have great gray-white contrast, or B0 regions. And so since those are already built into FreeSurfer, it's possible to say, this, rostral anterior cingulate is a high myelin or a high B0 region. And so I know where that is because FreeSurfer tells me where that is. So I'm going to exclude those vertices from my registration because I'm not getting good signal from there. So these are all things that can be done in BBR. So this is what the cost function looks like. So in this case, this is from normalized mutual information. So this is what SPM uses. This is something that was developed, I don't know, 1990 or something like that to do cross-modal registration. Has been kind of a standard in neuroimaging for a long time. So the way this works is that the x-axis is a displacement. So I have everything aligned perfectly, and then I displace the functional relative to the structural by, say, 1 millimeter. I say, what is the cost function there? And then I do it 2 millimeters, and then I do it 3 millimeters, and I do it on the other side. So, I'm basically moving the functional back and forth like this. And I'm looking at what the normalized mutual information cost would be. You can see that it minimizes there at 0, where everything is nice and perfect registration. And then, you get up here. So the way that the registration works would be, if you started off here at 5 millimeters, the registration program would say, hey, if I step here, I'm reducing my cost. If I'm step here, I'm reducing my cost. And it keeps following it down. And then it eventually finds its way to where the minimum is. So if you look at the BBR cost function, you see it has the minimum at the same place, but it's much narrower. And the reason for that is for the reasons that I just described, which is that you're only looking at voxels where you expect to actually have signal that can drive your registration. So with normalized mutual information, it's a whole brain method. So it's looking at every single voxel. And so what does that mean? When you look here at white matter, that's all basically constant. It's not telling you anything about, if you just had like a little window on white matter there, you'd have a little window in the anatomical, you'd have a little window in the functional, and that is not going to tell you how well you're actually registering those two together. Furthermore, you can get in all kinds of stuff in the white matter that might not agree between the anatomical and the functional. You have bias fields, you have various lesions, you have all kinds of stuff that's going on in the white matter that is then going to corrupt the registration signal. And that's why you're seeing this difference between the sharpness of the peak, or of the trough in this case, between the BBR and normalized mutual information. And this is important. So I did a noise sensitivity test. So here's the anatomical, here's the functional, this is at 2 millimeters. And then I just added progressive amounts of noise. And so I know where the registration should be based upon my registration to the uncorrupted fMRI. And so what I can do is register each one of those things and see how far it moves away from where I know the optimum is. And so in this case, I tested normalized mutual information against BBR. Horizontal axis is this noise level. And then the vertical axis is the deviation away from where I know the optimum to be. So with normalized mutual information, as I increase the amount of noise, I get a steady deviation from the optimum. However, with BBR, over this wide range up until this 130 value there, it's almost constant at about 0.2 millimeters. and then it starts to go up when you get to these extreme noise levels. And so this is the difference between these two, is because of the sharpness of this peak that I was just describing. So there are voxel size effects in the cost function. So this is the graph that I showed you before. This is 2 millimeter fMRI for normalized mutual information and BBR. When I go to 1 millimeter, you can see it with this this yellow curve here. You get something that's a little bit sharper. And so, so higher resolution is going to actually give you a little bit sharper of a peak and better registration accuracy. You can have parametric effects in BBR. So by that, what I mean is, you have these parameters that I was just describing, and there's a certain amount of play in BBR. So the way that BBR is essentially working, you can think of it in this way, is that it's creating two surfaces. So one surface is the white matter surface projected back into the white matter. And then the second one is the white matter surface projected into, say, the middle of cortex. And so between those two, there's a little bit of play. So you can imagine that that would create like a certain circumstance where you could move this thing around a little bit, and you're really not going to get a change in the cost function all that much. And so this is shown here. So this is the same graph that I had before. So NMI, BBR at 2 millimeters, BBR at 1 millimeter, and BBR at 1 millimeter, where I have tightened the those parameters. So if I come back here, instead of allowing, I think the default is 2 millimeters into white matter and half of cortex, half of the thickness into cortex. I reduced those so that now I'm sampling closer to where the white surface is, which is closer to where that contrast boundary is. And so when I do that, I again make it a little bit narrower. So there are limits to this, because the closer that you make that, the more likely you are that you're just going to be sampling the same voxel on either side. And so if you sample the same voxel on either side, you have basically a contrast of 0. So, at some point as you tighten the screws on BBR, it's going to start to fail, because there's not going to be any signal there, because you're just going to be sampling mostly from a single voxel on either side of the surface. So I did all these experiments to see how robust BBR was. And so one of these experiments was to look at this partial field of view. So what I did with this experiment was to take an fMRI volume and register it and get the kind of the gold standard for what the registration would be. And then I started removing slices, remove the top and bottom slice, remove the next slice, remove the next slice. So that's what this horizontal axis is here. So it starts at 30, goes all the way down to just a single slice. And then the vertical axis is how much does the registration move when I'm reducing this field of view. So I have, these are correlation ratio, which is what FSL uses, NMI, which is what SPM uses, and then BBR. You can see that for both NMI and correlation ratio, you're getting systematic changes as you reduce the field of view. But with BBR, it stays very, very small changes as you change the field of view. And this just shows the robustness of BBR, even when you're reducing the field of view. Oops. So there are non-rigid effects in fMRI between the anatomical and the fMRI. So there are numerous ways to try to address this. So one of the things that you could do is, instead of using a rigid transform, you would do an affine. So an affine would add a little bit of scaling and a little bit of shear. So that maybe that's enough to account for the distortions that you're seeing. If you have a B0, you have B0 distortion, and you can collect a B0 map. But what happens if you don't have a B0 map, or you suspect that your B0 map is not collecting all the B0 distortion? So this is just a reminder, I'm sure you all know this, that B0 can cause dropout in your fMRI. It can also cause stretching. So you have this metric distortion and you have intensity distortion. And both of these can affect the registration, especially the dropout, because dropout means that there's this inconsistency between the anatomical and the fMRI. So if you're doing, basically all the registrations are always going to assume that there's this consistency between your anatomical and your functional. And so this is an inconsistency that will hurt your registration. And of course, once you have metric distortion in there, that's an inconsistency that's incompatible with a rigid or even an affine model. So you can collect a B0 map in various ways. This just shows the 2-echo method. And from that, you can create a voxel shift map. So this is showing you the amount that a given voxel is going to shift relative to its true location in the anatomical. So if you have these types of maps, BBR will take this as input in addition to the surface and the fMRI volume. And what it will do is it'll see how much of a shift there is. It will shift the surface to sample the fMRI in the proper location. So it's not resampling the fMRI, which would potentially cause interpolation artifacts. It's shifting the actual surface. And then in FreeSurfer, when you're applying this, it actually shifts the surface to sample the fMRI, so you're not having to get some kind of smoothing due to interpolation. So another way around this would be to do this piecewise registration, as Van Morik suggested. So basically, you're just dividing the fMRI volume into subvolumes and then doing rigid or affine registrations within there, and then kind of putting it all together to sample your surface on. And finally, one possible method is to treat. So what BBR is basically doing is that it's placing the surface on the fMRI. And this is what FreeSurfer or CAD or Brain Voyager are doing on the anatomical. Like this is what FreeSurfer does. It takes an anatomical and it places the surface based upon certain criteria onto the anatomical. So the question is, okay, why go through all this stuff with the fMRI? Why don't we just place the surface on the fMRI? And so the way that you could do that. Sorry, Brain Voyager also. I'm not sure. Brain Voyager uses BBR. Is that the statement you were making? Yes. Yeah. I think I said that, didn't I?
Oh, thank you. I think that may be a misunderstanding. I think Doug was talking about how to create the anatomical surfaces. Yes.
Yeah. Sorry. So what BBR is doing is it's placing a surface on the fMRI. And so the question is, why go through this whole registration procedure that may or may not be accurate depending upon what your B0 distortions are? Why not just simply place the surface on the fMRI without going through this intermediate, or without assuming that things have to be rigidly aligned? So to do this in FreeSurfer, you would start with the FreeSurfer surfaces. placed on the anatomical, you would bring those surfaces into the fMRI space through an affine or rigid registration, applying B0 distortion if you happen to have a B0 map, and then use the standard free surfer replacement. So I actually tried this at John's behest when I was putting this together, and we met like a few months ago to talk about what this lecture would look like. And I said, "Oh yeah, you could maybe do this method." So I quickly, I think on Monday, uh, actually did this. So here's the surface placed on the anatomical. This is the white matter surface that's transferred to the MRI, and then I just plugged this into FreeSurfer and just to see like and let it adapt the surface the same way that it would place it on a T1. And unfortunately, it didn't work very well. It didn't completely catastrophically fail, but you can see like a lot of places where this red line is following the yellow line, but there are other places where it's just doing something crazy. So this method did not work super well, and granted, I only did this yesterday, so there could be a lot more things that we can tweak on. So we could impose more constraints, such as forcing it to only adapt the surface in the phase encode direction, because B0 distortion is generally only in the phase encode direction. Or if you could acquire a better quality image. So the fMRI tends not to have like tons of gray-white contrast, and back in the day, 20 years ago, when people were scanning here, they would acquire something called a T1 EPI. And that was actually a decent T1 weighted image that had all of the distortion that the standard functional had. So you could do something like that, or do like, or maybe use a spin echo so that you're not getting this dropout. And if you could get a decent image like that with good gray white contrast and not a lot of dropout, then I think it would actually it's actually pretty easy to apply it in this way. So there are some limitations on using BBR. So you should not use it on volume smooth data. So I know that everybody in here is very interested in Cortex, and the last thing they would want to do is to smooth their data in the volume. But which also describes me, but I also do a lot of PET research, and I was quite shocked to see that certain biases can creep into the registration when registering PET data to an anatomical, and this is because there's this interaction between the anatomy and spatial smoothing that can corrupt the signal. It's basically a partial volume effect, which I'll talk about this afternoon. In addition, you can get this dropout along the edge of the brain. So as was described yesterday and today, at the edge of the brain, you have all of these veins that are there, and those veins have a lot of deoxy in them. And so you end up getting a lot of dropout right at the edge of the brain. And so this can sometimes corrupt the contrast that that BBR is trying to measure. So if you remember that contrast curve, you're expecting contrast in a particular direction, that gray matter is brighter than white matter. But off here in the edge, you might have situations where gray matter actually becomes darker because of this dropout. And so to summarize here, we obviously need extremely high accuracy registration for laminar analysis. But we are challenged by bias fields and partial fields of view and distortion. BBR exploits this knowledge of the anatomy, in particular where the surface is, to give the most sensitive and robust cost function, and that we only use voxels that are relevant for registration. No need for brain masking, no need to sample data in the heart of the white matter. We're only registering cortex, but if it's an affine registration, then that's going to be good everywhere. You have parameters in BBR that you can tweak to try to improve the registration. But I kind of played up this idea that you can tweak these parameters to get a better, a sharper cost function on it. But if you looked at all those cost functions I showed you, a lot of them were just the same. And that's one of the nice things about PBR is that it's very robust. You can change all these parameters. You can change voxel size, you can change field of view, you can change bias fields on it. And the cost function just kind of doesn't care. You can get a little bit better, something that's a little bit narrower. But that's the nice thing about BBR is that tweaking these cost function parameters doesn't generate a huge change in the topology of the cost. And finally, you have B0 distortion, and the B0 distortion is a real thing. I know that Divya is going to talk about that this afternoon. But you can easily get 2, 3, 4 millimeters of shift due to B0 distortion, and that's easily enough to just throw you way off of cortex in those regions. And you have this dropout, which becomes an inconsistency between the anatomical and the fMRI, and that will also throw things up. So that's all I have. So I guess we can break a little bit early. I can take questions. Thanks.